Okay, so let's see. I already upload in the WhatsApp group. Okay, you can download. Sorry. So if you look at here, okay, we will discuss on the stress and strain under axial loading now. So for this part, actually, yeah, by using a statistic is not how to say. When you want to what is it? Not develop, build the structure, right? Okay. Also the machine, right? Actually, there is a deformation is occur, okay, in the structure or in your truss. So, um, we for this part, we will calculate mainly how to calculate the deformations, okay, by using the symbol is delta, okay. For example, this chapter is we more to devoted to the study of the deformations, okay, under the structural component, okay. So mostly subjected to the axial loading, okay. For example, the change in the length, okay, once you press or you pull the you give a force, okay, especially like in the design of the bridge, right? Okay, so there's gonna be deformation occur, okay, or your machines like drilling of oils, right? Okay, so petroleum, okay, the machine have the deformation occur, okay. So for this part we will focus on the deformations, okay. So what we're gonna learn is stress and strain diagrams, okay, deformation under axial loading, okay, for statically determined structure and indeterminate structure, okay. So I hope that later you can know how to calculate the stress and also deformations, okay. So if you look at here as a background that the string of the red pipe suspended from this traveling block on an oil rig is subjected to extremely large loading and axial deformations. Okay, inilah. Okay, untuk pipe this one. Okay, so only if you have knowledge of static is not sufficient, okay. Suitable of the structure or machine depends on the deformation in the structure, okay, as well as the stress induced under loading. So as I told you that static analysis alone is not sufficient. So we need the knowledge of the deformations. So if you look at here that we already determines, okay, the stress distribution within the member also required consideration of deformation in the member. So I think we focus more to the stress distributions, okay. So what we need is the consideration of the deformation. And then this chapter, okay, we concern with the axial loading and also the deformation. Okay, so member under axial loadings, like we pull or we press, okay, is compressed, compress or tension. Okay, sorry. Chapter 3, we will deal with torsional load and also angle of twist. Okay, it's also deformation, angle of twist. Okay, but more to like we apply in by moments, right? Okay, this is a torsional loading lah. Okay, so if you look at here, okay, if we consider root BC, isn't it? Okay, root BC, okay, with the length of L. Okay, this is L. Okay, and uniform cross sectional area. Okay, is a uniform. Okay, so we suspended. This is a road C, right? We suspended here on the road B, which is a fix, right? Okay. So once we apply the force, okay, P, force as a P, okay, to the end of the C here, okay, right. So actually the road is elongated, okay, it's elongated. It become because you pull, right, okay. So actually we can plot this graph, okay, from this one, okay. If you plot, okay, once you pull, right, okay, there's a steep here, okay, and then some like this lah, okay. If your material is a ductile material, it's not brittle, okay. It's difference the graph is between the brittles and also ductiles lah. Okay, so this one the elongation lah, delta. Okay, and then this is the force lah. Okay, delta against the pressure. This is the delta is we call it as deformations, okay, against the pressure, okay, or force. Okay, so elongation is delta. This is what we call it as a stress. Okay, okay. In order to determine the normal strain, epsilon equal to delta divided by L, the length. But this one is P divided by A, the area lah, cross sectional area. Okay. So this one we can predict the deformation. Okay. Okay, if we deformation delta, okay, this one is produced from the road BC. Okay, how about if we apply a force, okay, double, okay, 2P, okay. So this is, I mean, for if we apply 2P for the cross sectional area is 2A, we double the cross sectional area for B prime and C prime, right? So if you look at here, the same length, okay, it's going to produce the same deformations, okay, although is the force is double and area is double, in terms of ratio is the same, okay. For the normal strain also the same, okay. So this for the both case is going to be the same, the deformations or the stress, okay, it's going to be the same. Okay, and if we increase the length, right, B prime and double primes, okay, and C primes, okay, and then we apply force P, is going to be the same, okay. Normal strains also, the ratio is going to be the same, okay. From this one, actually, we can define the normal strain, okay, under axial loading, okay. This is the deformation per unit length lah, okay. So this is what we can define based on the normal strain, okay. So just based on this graph, okay. So how can we measure these deformations or the normal strains by using the machines, tensile machine? I think if you have a lab thermodynamics and materials engineering, you will conduct this experiment, like the test specimen with this tensile. So you gonna pull this materials, okay. So the material is depending on the properties, whether it's ductile or um, brittle, okay. Because for brittle is easy to rupture, okay, rather than ductile. Ductile is going to be elongate first before it rupture, before it spill, okay. Okay, so let's see the difference between the ductile material as well as the brittles, okay. If you look at here that we saw here that this is for the ductile materials. It is characterized by their ability to yield at normal temperature. Okay, for example, steel, alloys, and metal. Because of, if you learn in chapter 2, right? Okay, the previous chapter, this is due to the one is the chemical bondings. Okay, you know, depending on the different in electronegativity also. Okay, so it's different for the steel and different for the time material. For example, is glass, iron, right? It's easy to break, okay. It's easy to rupture, okay. So if you look at here, okay, for the ductile materials, okay, for example, steel, okay, and other alloys, okay. Since we characterize the ability to yield, okay, we try this by using we test with the machines, okay. So when we increase the load, right, we give a load, we pull this one, we pull, right, pull, okay. If you look at here, the length is increased, right, okay. This is a normal strain, the length is increased, okay, linearly, okay, when we increase the load. So meaning that is a proportional at very slow rate, okay. So if you look at here that the graph for the stress and strain, right, this is a stress and this one is a strain, is this straight line, okay, which is we can see is a very steep slope, okay. However, after the critical value, okay, this one is sigma y lah, okay, of the stress has been reached. If you look at here that the specimens undergoes What is it? What we call it as a large deformations. This is a yield, and this one is strain hardenings. Okay, so we can see this is the maximum lah. Right, there's a neck, like a neck shape, right? Okay, when we apply the loads lah. Okay, so this one is there's a like two typical ductile materials. Okay, there's like this one lah. Okay, and then yeah, of course, elongations uh, actually is become more lah. Okay, until we reach this one. This is what we call it as a necking lah. This one necking. Okay, until we reach the maximum one. This one is delta B, right? Okay, so if you apply more loads, only a very small load is going to be rupture. This one. Okay, is breaking the strength lah. Okay. So this is what we call it as the graph for the ductile materials. Okay. Okay. So if you look at here that usually for the necking, okay, this one is if there's a necking right here, okay, generally is 45 degree lah. Is a necking. Okay. Okay. So this is in terms of the time meters. So how about the brittles? Brittles there's no shape like a ductile. Okay. When you pulse, it's rupture until the end. There's no elongation like this one. Right? Okay. That's why a cast iron or a glass stone, or the glass lah, right? Just drop, it just break the glass. Okay, rupture occurs without any noticeable prior change in the rate of elongation. This is the difference. Okay, for the brittle stain at the time of the rupture is much smaller than for the ductile materials. Okay. Okay. Any questions? The difference between is it the ductile and also brittle materials? It's clear, right? Okay, so let's see deformation under axial loadings. Okay, actually we use the Hooke's law. Okay, this one. Okay, so how to calculate the deformations? Okay, of course we need the deformations, right? This one. How to calculate this one? Okay, from the sigma equal to E. Okay, this is Hooke's law. Okay, and this is a modulus Young, right? Okay, times to the E. So just substitute into this equations. Okay, so we can get equation for the deformation. So meaning that P is the axial loading force, L is the length. Okay, A is area, and E is modulus Young for all the materials. Okay, this is for one materials, but if you have a variations in loadings, okay, and variation in cross-sectional area, as well as different materials, so you have to summation of PI, LI, AI, and also EI. I is the represent for the materials or different loadings. Okay, so meaning that P1 L1 divided by A1 E1 plus P2 L2 divided by A2 E2 plus and so on PI. Okay, until Pn lah. Okay, so variational. Okay. Elastic deformation of the axially loaded member. For the constant loads, external force is applied at each end of the members. It's going to be sign convention is opposite. Okay, so if you look at here that this one is positive. Okay, tension or elongation, but negative for the compression or the contractions. Because this one you pull, right, and this is going to be if you add this two, it's going to be cancelled out. Cancel. Okay, it's become 0. Okay. Yeah. Okay, so let's see the example. Okay. Um, let's see the example, this one, right? Okay. Determine the deformation of steel rod shown under the given loads. Okay, is given modulus Young is 29 times 10 6 psi, D naught and DI. Okay, 1.07 inch and 0.61 inch. We have to calculate the deformation. So the procedure, of course, similarly. Okay, you have to draw the free body diagram. Without free body diagrams, you cannot imagine how the force is where is the direction of the force, right, and number of unknowns. Okay, divide the rules into component and the loads applications. Okay, this is a free body diagram. Apply free body analysis, okay, by using a method of section to determine internal force, and then evaluate the total of component deflection or deformation. Deflection is deformation. Okay, so if you look at here, that so we divided into three components. Okay, we choose from the right side. Okay, right, this is already explained just now, also already explained how to do this cutting, okay, for each section. Okay, well, you have to draw this one vertical line, this one vertical line. So you can imagine the internal loading towards which direction. Okay, this one kilopascal keeps not kilopascal, keeps is in US units. Okay, inch per square, kilo inch per square. Okay, so just calculate. And if you look at here, right, for L1, this is L1, right? This one L1 is 12 inch. Okay, let me check. Sorry. This is 12 inch lah. This is 12 inch, 12 inch. L1, L2. This one L3, 16 inch. Okay, L1, L2, L3. And area for 1 and 2 is the same, 0.9 inch square and 83 0.3. So meaning that they have a difference area or difference diameter. Okay, so you have to use equation this one because difference cross sectional area. Okay, this is only one material or one area, right? This one summation of all the force and also length area. Okay, so if you look at here, that we have to determine the unknowns 1 2 3. So this one PAB is this one. This one PCD. This one is PCD. This one is PBC. This one PAB. Okay. 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 And then three. Once you determine. So if you look at here, this one is 30 kilopascal, but this one negative 15, meaning that is the opposite direction P2 to that direction. Okay, is a opposite. Okay, and this one is correct. Okay, okay, and then you add summation. PAB, this one, right, this one, and PBC, this one, and this one. Okay, and then this one and this one. Okay, okay, so we can get 75.9 times negative 3 inch. Okay, the deflection. Okay, also this is 0.075. Very small. Okay. Okay, any questions about how to calculate the deflection or displacement? Okay. Deflection, deformation, displacement. Sama lah. That is the same. The synonyms. Okay. Clear? Okay. Thank you. John Tiger. John Tiger. Oh, John Ting. I thought John. Sorry. John Ting. Sorry, John Ting. Okay. Uh, as we move to the example two. Okay. Determine the internal force for each segment and the displacement of NA with respect to ND. Okay, what do you mean by respect this one? Okay. So one is we have to set it as a fixed lah. Okay, as a fixed point. Okay. This is just indicate relative displacement. Okay. For example, if we have a fixed support here, use fixed support, right? Fixed support lah. Dia dekat dinding kan. Okay. So we can use delta A lah. But if this one, you see there's a two force here, right? Okay. This is meaning the displacement of A relative to D. Okay. Relative to D lah. Okay. Meaning that relative displacement. Okay. So we just consider as we just imagine there's a fixed support on the point at the point D. Okay. So assume the 3 meter bar is made of steel, E equal to 200 gigapascal. Each segment is equally divided. Cross sectional area is 1 meter square. Okay. What you have to do, of course, okay, you have to draw free body diagram. Okay. So if you look at here, that this one, this one, this one. Okay. This one. Okay. If displacement of D relative D relative to A, meaning that you have to start from this direction. But this one relative A relative to D, so we start from the left lah, from point A. Okay, so we assume this one is fixed lah. Okay, we assume. Okay, you understand? Okay, so by the method of the section, definitely you have to calculate this one is a P AB. This one is 5 kilonewton, right? Of course, you know this one 5 kilonewtons. This one is 5 kilonewtons. Because there's a 8 kilonewtons here. Don't forget. At the center also have a this one should be there's a force here now. So meaning that PBC equal to plus 8 minus 5 equal to 0. So you can get PBC lah. Okay. 8 tolak 5 3 equal to negative 3 kilonewtons. So because you assume this direction, so meaning that is going to be opposite direction. So PBC equal to 3 kilonewtons. Okay, this direction positive. So meaning that opposite direction. Because we assume to the right side, right? But the correct one is to the left side. And you do the same thing for CD lah. Okay. So if you look at here that this one is the solution, right? See, this one also actually you can calculate. Look at here. This is 7 kilonewtons, right? Okay, because they choose on the right side, but it's the same also. If you want to calculate from here, you cut until here, right? Okay. So what you have to do, PCD equal to minus 5 plus 8 plus 4 plus PCD. PCD lah. Equal to 0. Apa tu? 7 ya? 7 kan? Okay. 7 lah. Okay. PCD equal to 7. Hmm? So meaning that this direction lah, because you will get negative here. Okay. So if you calculate this one toward this direction lah, this direction lah, because you calculate choosing left side. So meaning that is the opposite side. Same. It's the same. Okay. Same. So it's compression. Okay. BC compression, AB tension, CD compression. And then the same things, okay, what you have to do by using delta AD. You have to use this one, okay, AD, because it's relative to the point D. A relative to point D, the displacement. Okay, just substitute 5, -3, -7, okay, AE, 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 okay, and the same, because the same area lah, okay, only L is a difference. So you can get displacement of point A relative to B. Okay, about to -25 nanometer. Okay, so meaning is compressed. Okay, because there's a negative here. Okay, so if you look at here, that displacement of N A with respect to N D. Okay, if all other data subjected, if you look at here, positive, meaning that it elongates. Okay, which is this one lah. There's a tension lah. Okay, so means A move toward D. This one is negative, is a shorten. Okay, because it's compressed lah, because it's negative, right? Okay, double subscripts AD is relative displacement, which is A to D, point A to point D. If single subscripts, this one relative to speed point, meaning that your truss or your members is there's a fixed support here. This one, this is point A lah. This there is a fixed support here. Okay, so meaning that what we call it that is suspended lah. Okay, or suspended lah. Yeah, it's fixed point lah. Okay, also like this, suspended also. Any questions? Is it clear, or you want to stop? Or you want to continue? Is no, doctor. Okay, no, clear. Okay, all clear, right? Okay, just another one examples and tutorials we discuss next class lah. Okay, next class 1 hour we discuss the tutorials, but the solution also I will included already this one in this PowerPoint slide. Okay, all the solutions. I think this is the important example lah. Okay, just very short one. This is this kind of how to say problem yang selalu I will create for the final. Okay, using the algebra and trigonometry. Okay, if you look at here, that the rigid of bar BDE, okay, BDE is supported by links AB, right? This one and CD. Okay, link AB is made of aluminium. What is it? This one aluminium, right? AB, this one, and then CD is a steel. Different materials. Okay, cross sectional also different. A 600 and 500. 500 is for AB and CD is 600. For the 30 kilonewton force, determine the deflection at point B. This one, point D, and also point E. Okay, the deflection. Okay, so we apply force here, 30 kilonewtons, right? You apply. So meaning that when you apply force, okay, because it's different materials and different cross sectional area, so the center is, if you look at here, like the center of this one, when you apply force, for example, so it's gonna be this bar is, this one is gonna go up, this one is gonna go down, right? Okay, is it? Okay, so meaning that your bar is gonna be here. This is the bar. Yalah. Okay, it's moving. Okay, and then this still this is just imaginary of how to say the original position now. Okay, okay, okay. So I just guess like this one now. Dia akan memanjang macam ni lah. Okay. So yang ni naik ke atas kan? This one is gonna be this side. Okay. This one is gonna be to this side lah. Okay. Okay. So your maybe like this lah. Okay. Okay. So the original one is gonna be this one. Because you apply force. Right. It's maybe the point of how to say this one. So meaning that we have to point the problem is deflection at point D, this one, point D. Because not the point of how the cross is not really at point D. Okay. There's some here lah. If this one is point D, right? Something like this. Okay. And ada deflection lah. Okay. This is point D lah. Okay, how to find the deflection at point D actually. Okay. So what we have to do is, of course, we have to draw free body diagram first. For me, I will draw this one first lah. This one, this free body diagram. Okay, B, D, and also E. Because we need the force for the A, B, and also C, D lah. And then we have to find the this displacement of the points A, and this one also, C, D, okay, and also E lah. Okay. So apply free body diagram. This is a step. Evaluate the information and work on the geometry lah. Okay, if you look at here, right, this is a free body diagram for each member. Okay, B, C, C, D, this one. This one is we already explained. So if you look at here that total F, because there's a two unknowns on the y direction, that's why we use more moment. This one is moment at point B, so we don't need to calculate FAB, but only FCD and 30 kilonewtons, so that we can get 90 kilonewtons. And point D, another one, right? If you want to do at the point E, also possible after you determine the FCD. Okay, it doesn't matter at the point D or point E. So you will get the same answer, 60 kilonewton. So this one is a negative, also meaning that this is a compressed and this one is then tension, positive. Okay, so once you determine FAB, okay, this one 60 kilonewton and this one is 90 kilonewtons. So we have to determine the displacement of the member AB and also CD. So we can get displacement D and B lah. Okay, but the problem is this one. Okay, you have to use the geometry because we want to determine the displacement at point E. This one. What is the displacement, right? Okay, so this is the graph. This is the original bar. Okay, the position, original position. When you apply 30 kilonewton, is going to be how to say, is a displaced lah. Okay, displaced to certain distance. Not distance. Okay. Panggil apa? Jarak lah. Okay, distance, right? Okay. So if you look at here, this one, right? This is point D lah, here, point D. And this is the cross, I think the center here, around here. Okay. Okay, yeah. And the problem we have to determine this one, right? Okay. For the displacement of point B and also point D, okay, this one we already determine here, this one, by using this one. Okay. But the problem is point in. Okay. So what we have to do is, if you look at here that this is a BB, okay, BB, B prime and BH, this one. Okay. So divide by DD and DH, just based on the ratio. Actually is we do like this one, right? BB prime divided by BH, okay, equal to what? Because this is the same length, this one is the same ratio. The same ratio. It's the same ratio. Okay, and then this one is D prime divided by DH lah. Ratio is going to be the same. Ratio is going to be the same, right? Because of the deflection. Okay. This one divided by this one, and divide by this one, right? So just rearrange, go to here, and this one go to here. So you can get this one. Okay. So if you look at here, B prime is 0.514. Okay. 0.14. This one. BB lah. This one. This one, right? And then BH. Wait. BH, wait. Okay. And then DD. Okay. 0.3 lah. This one. Displacement at point D. Right. Okay. For the BH and HD, if you look at here that because of this one is 200 meter, right? The length between point A to point B to point D, this one total. Okay. So if you assume, because this one is point H, right? This one we assume as X. This one is going to be 200 minus X. Okay. So meaning that this one is going to be 200 minus X. This one is X lah. This one. So if you look at here, just rearrange lah. You solve it because the X is the same. So we can get X 73.7. Meaning that this one lah. Okay. The same method, which is a trigonometry, you apply also for point E. This one, and also point D, this one. Okay. So if you look at here, right, E, this one and also this one until here. DD, this one is lah, right, and then HE, this one lah, total. Okay, and HD. Sorry, this one. EE until here lah. This one is HE. Okay, this one. So displacement of E. This one is displacement E, right? Okay. So just rearrange, we can get displacement 1.9228 millimeter. Okay, it's positive, right? So it's tangential. Okay, is it clear? Okay. Generally, I'm not sure. I'm not prepared this question, I think. Okay, I like to use this kind of problem. Okay, for example, how to say last year, 2 years ago, so I did the similar things. Okay, any question about this one? It's just a trigonometry. This example also trigonometry. See, it's mathematics. Any question before we stop? Okay, I think I guess it is clear. For final answer, draw arrow to right. Please see. Total for final answer is draw arrow not right, T or C. Just arrow. This one is the direction. Okay. If you want to this one, right? Positive, it elongates. Is I don't think we use tension or compression. If deflection, elongates or shorten. That's all by using arrow. Okay. For this one, because it's the deformation. For force, yes, tension and compression. But elongation is more to arrow lah. This one, of course, we can imagine. We can give a clear, what is it, a picture, right, towards downwards, right, right, rather than because you apply force at 30 kilonewton. Okay. So is meaning that elongates or shorten. If force, yes, tension and compression. Okay. Okay. I guess my explanation is clear, so we just stop lah. Okay, we stop. We continue. Can you share the attendance once again? Okay. So I share the attendance. Thank you very much, everyone. See you again for the next class next week. So we will discuss this chapter and also chapter 3. Very short. Okay. By next week or another 2 weeks, we will finish. Thank you very much.